Wet detention ponds are a cornerstone of water quality control and are among the most frequently utilized best management practices, or BMPs. While their initial design and implementation were primarily focused on flood control, observations revealed a significant change in pollutant concentrations between the inlet and outlet of these ponds. This crucial finding demonstrated a clear relationship between the residency time of water in the pond and its ability to reduce pollutant loads. Further documentation solidified their value, particularly in controlling total nitrogen and total phosphorus, directly linking their effectiveness to the presence of a permanent pool of water within the pond structure. Our primary goal in this module is to equip you with the knowledge to accurately assign an annual removal effectiveness to wet detention ponds. We'll explore the various conditions that significantly affect this removal, including residency time, the impact of floating wetlands and managed aquatic plants, and how upstream retention might influence the pond's overall effectiveness. To help us analyze these factors efficiently without extensive hand calculations, we will be utilizing the BMPFast software. We'll start by defining what a wet detention pond is, then move into navigating the BMPFast software, specifically demonstrating how to use its worksheets in relation to these ponds. We will also investigate different options you have to change and enhance a pond's performance, applying these concepts through practical example projects to solidify your understanding. A wet detention pond, as its name implies, is an impoundment designed to hold water year-round, maintaining a permanent pool. Its main purpose is the collection and temporary storage of stormwater. This design facilitates the treatment of stormwater through a combination of physical, chemical, and biological processes before the water is gradually released. A key feature is this permanent pool, which is measured from the normal water level, frequently at the lowest pond discharge elevation, down to a depth that ensures the pond water remains oxygenated. In some instances, anoxic depth is specifically calculated to help define the volume of this permanent pool. The effectiveness of a stormwater treatment system is largely a function of its average annual residence time, or ART. Put simply, as the average annual residence time increases, so does the system's effectiveness at removing pollutants. It's worth noting that pollutant removal is generally more rapid during the first day, primarily due to particle settling, compared to the longer term. The annual residence time is calculated by taking the volume of the permanent pool, measured in acre-feet, and multiplying it by 365 days per year. This product is then divided by the annual runoff, also measured in acre-feet per year, to give you the ART in days. Therefore, you can influence the ART by adjusting either the permanent pool volume or the annual runoff into the system. These effectiveness curves, such as the separate ones developed for total phosphorus and total nitrogen, were derived from existing ponds that typically include a littoral zone. A littoral zone, with its shallow water and emergent vegetation, plays a significant role in pollutant removal. If a treatment system does not have a littoral zone, its removal effectiveness will be reduced. To account for this, you can adjust the removal value obtained for a system with a littoral zone by dividing it by 1.1. When considering wet detention pond designs, we have several important configuration options. One key factor is the average annual residence time, or ART. This value is calculated based on the permanent pool size and the annual runoff. While the applicant's handbook specifies an upper limit of 200 days for the ART, it's important to note that some local and legacy programs may allow for a higher number, and design tools like BMPFast can accommodate these variations. Beyond the ART, other design choices include the incorporation of a littoral zone, the strategic placement of floating wetlands, or the use of other managed aquatic plants, such as an expanded littoral zone. Specific guidance regarding features like floating wetlands is provided within the applicant's handbook. Regardless of which plant options you choose, whether floating wetlands or littoral zone plants are utilized, it is crucial to remember that all these pond systems require ongoing maintenance to ensure their continued effectiveness. While the annual residency time, or ART, can be calculated to be quite high, for many regulatory and calculation purposes, it's often capped at a maximum of 200 days. Let's look at an example. Here, we have a permanent pool volume of 2.3 acre-feet and an annual runoff of 2.581 acre-feet per year. When we calculate the actual ART using the formula of permanent pool volume multiplied by 365 days, then divided by the annual runoff, we get an ART of 325 days. However, when using software like BMPFast, which incorporates current regulatory and practice information, the ART would automatically be adjusted to a maximum of 200 days. This means that even if the physical retention time is longer, for the purpose of estimating annual pollutant removal effectiveness, we use 200 days as the upper limit. For a standalone pond that includes a littoral zone and operates with an ART of 200 days, the annual removal percentages for total nitrogen, or TN, are typically 43%, and for total phosphorus, or TP, they are 80%. These values are rounded to the nearest percentage. It's important to note, however, that in some specific cases, especially for older best management practices under certain Basin Management Action Plans, or BMAP programs, an ART greater than 200 days may still be allowed for calculation purposes. Under certain circumstances, or when research on performance is needed, an average retention time, or ART, greater than 200 days may be allowed. The BMPFast software specifically allows for these extended ARTs by providing an option to generate removal calculations for these scenarios. It's important to note that if these calculations are to be used for a permit, mutual acceptance of this extended ART must first be obtained. When extending the ART beyond 200 days in BMPFast, you'll observe a specific change in the pollutant removal efficiencies. For total phosphorus, or TP, the removal rate increases from 80% to 84%. However, the removal efficiency for total nitrogen, or TN, remains consistent at a rounded 43%, similar to the removal at the maximum ART of 200 days. When evaluating the efficiency of best management practices, particularly detention ponds, placed in series, it's important to understand how pollutant removal truly works. A common misconception is to simply add the removal efficiencies of each pond. For example, if we have 2 wet detention BMPs in series, and each has a 50-day residence time, you might intuitively think that if one pond removes 40% of total nitrogen and 68% of total phosphorus, 2 ponds would simply double those numbers. However, this is incorrect. The fundamental principle is that pollutants removed by the first pond cannot be removed again by the second pond. Once a pollutant is removed, it's gone from the water column, entering the downstream system. Instead, when 2 ponds are in series with no additional input between them, they effectively function as a single system with a combined residence time. So, 2 50-day residence time ponds operate more like one large pond with a 100-day residence time. When we look at the efficiency curves for a 100-day residence time, the removal would be approximately 42% for total nitrogen and 74% for total phosphorus, which is not double the individual pond's efficiency, because the upstream BMP significantly impacts the effectiveness of the downstream BMP by pre-treating the water. We cannot use equation 9.5 from the applicant's handbook, Volume 1, Appendix O, for calculating the combined efficiency of detention ponds in series. The general principle applies across all treatment BMPs. You cannot remove the same pollutants more than one time from the same water volume. Therefore, doubling the permanent pool volume by adding a second pond in series does not double the pollutant removal. Floating wetlands offer a significant benefit in improving water quality. Studies have shown that even with a modest 5% pond area coverage, these systems can provide an additional 12% reduction in pollutant concentration beyond what the pond already achieves. To illustrate this, consider if a wet pond initially reduces the inlet concentration of total nitrogen from 1.0 to 0.6 milligrams per liter. If floating wetlands are then introduced, they provide an additional 12% reduction to that remaining concentration. This means we calculate 12% of the 0.6 milligrams per liter, resulting in a final concentration of 0.528 milligrams per liter, rather than simply subtracting 0.12 directly from 0.6. It's also worth noting that some review agencies recognize the value of additional area coverage combined with a robust maintenance plan. For instance, with a maintenance plan and 10% pond cover, a 20% credit has been used, provided an alternative best management practice is available if the 20% target isn't achieved. And as our 3P puppy reminds us, proactive maintenance is absolutely critical for these systems to consistently achieve and sustain their credited performance. These findings are supported by research from Wanyalista and the Florida Department of Environmental Protection, as detailed in the sources listed. When we treat pollutants in a series of best management practices, it's crucial to understand how their efficiencies combine. This diagram illustrates how the series equation, specifically equation 9-4 from Appendix O of AW Volume 1, is applied to calculate the combined removal efficiency. This equation is used because it assumes each downstream BMP acts independently of the upstream BMPs. This is particularly relevant when using technologies like managed aquatic plants or floating wetlands, as their removal efficiency isn't affected by the initial treatment from the pond itself. Let's walk through an example for total nitrogen removal. Imagine we start with 100 milligrams of pollutant. The first BMP removes 43% of this, leaving 57 milligrams. Now, the second BMP comes into play. It removes 12%, but crucially, it removes 12% of the remaining 57 milligrams, not of the original 100 milligrams. This amounts to 6.84 milligrams removed by the second BMP, leaving 50.16 milligrams remaining. As you can see, the total removal efficiency is 49.84%, not a simple sum of 43% plus 12%, which would be 55%. The combined efficiency is calculated using equation 9-5 to 0.43 for the first BMP, plus the product of the remaining pollutant after the first BMP, which is 1 minus 0.43, or 0.57, multiplied by the second BMP's efficiency, 0.12. This works out to 0.43 plus 0.0684, resulting in a total combined efficiency of 0.4984, or 49.84%. This method accurately reflects the cumulative reduction when BMPs operate independently in a series. This slide illustrates example efficiency curves for a detention pond, specifically showing how its performance functions in relation to the annual residence time, or ART. A key element here is the inclusion of managed aquatic plants, or MAP. You'll notice that you can receive up to a 20% credit for MAP, but this is contingent on having greater area coverage by the plants and a more frequent replacement plan. This immediately highlights the necessity of a robust maintenance program to ensure these plants contribute effectively to the pond's efficiency over time. Much like other visuals we've discussed, this plot serves as a valuable discovery tool within BMPFast. It enables you to visualize how annual pollutant removal efficiency varies as you adjust the annual residence time. This particular example depicts a pond designed with a littoral zone, enhanced by the presence of these managed aquatic plants. Finally, observe that the maximum annual residence time shown for this specific curve is 200 days. When we have best management practices, or BMPs, arranged in a series, particularly when an upstream BMP provides retention, it significantly impacts the effectiveness of downstream practices. For instance, if particulates are removed upstream, a subsequent wet pond will see its percentage removal efficiency reduced. This reduction applies to particulate nutrients, with a maximum adjustment of 20% for phosphorus and 10% for nitrogen. The actual fraction removed upstream depends on the treatment depth, so this maximum reduction is adjusted proportionally to the upstream annual removal. To calculate the overall efficiency of such a treatment train, meaning multiple BMPs in sequence, we use the equation shown here. This equation calculates the overall treatment train efficiency by considering the individual efficiencies of each BMP, E1 through EA. Let's look at an example to illustrate this. Imagine a scenario where we have 50% total nitrogen, or TN, retention upstream. followed by a wet detention pond with a standalone removal efficiency of 38%. We can use equation 9.5 here because the removal mechanisms are different, and this equation accounts for the change in the inlet concentration to the downstream BMP. In this example, the upstream retention adjusts the downstream wet pond's removal efficiency from 38% down to 33% because there's less total nitrogen available for it to treat. Now, applying the overall efficiency equation, we calculate 1 minus the product of 1 minus the upstream efficiency and 1 minus the adjusted downstream efficiency. This gives us 1 minus 0.5 times 1 minus 0.33, which equals 1 minus 0.335, resulting in an overall treatment train efficiency of 66.5%. The diagram visually represents this, showing how an initial 100 milligrams is reduced to 50 milligrams by the upstream retention, and then further reduced by the adjusted downstream removal of 33%, leaving 33.5 milligrams remaining. This example clearly demonstrates the importance of adjusting the downstream removal effectiveness. We must account for the change in pollutant concentration caused by upstream BMPs or other actions like on-site green infrastructure. Equation 9.5 is specifically used when the downstream removal effectiveness is obtained for the inlet mix of both particulates and dissolved pollutants. We'll delve deeper into the adjustment for annual removal based on concentration in the upcoming slides. When we talk about runoff, it's important to understand the role of particulates. The average yearly percentage of particulates in runoff can vary, but critically, many pollutants like nutrients, specifically nitrogen and phosphorus, and various metals are strongly associated with this particulate matter. Based on numerous publications and extensive laboratory analyses, an average yearly value of around 50% for particulates in stormwater runoff is a very reasonable estimate to consider. Now, let's think about what happens if we remove these particulates before they even reach a treatment system like a wet pond. From typical removal plots, we know that an untreated flow entering a wet pond might see about a 20% removal of total nitrogen and around a 40% removal of total phosphorus. If we assume that 50% of these total nutrients are carried in the particulate form, and we manage to remove all of these particulates upstream, before the pond, then the maximum potential reduction in the pond's overall effectiveness would be about 10% for total nitrogen and 20% for total phosphorus. This highlights the significant impact that upstream particulate removal can have on downstream treatment efficiency. This slide illustrates detention removal rates as they relate to upstream retention. We're looking at how removal works in a wet pond when there's a variable retention or treatment depth upstream. The key concept here is that the total removal is the sum of the upstream retention removal and the wet pond's removal effectiveness. This total isn't a simple addition. It's calculated using a series equation that accounts for the interaction between the two stages. Let's consider an example for total nitrogen adjustment with an average retention time, or ART, of 31 days, if we have 80% upstream retention removal. The calculation proceeds like this. We start with the 80% from upstream. Then we add the remaining percentage, which is 100% minus 80%, or 20%. This 20% is then multiplied by the difference between the wet pond's initial removal capacity, which is 38%, and the reduction in its effectiveness due to the upstream removal, which is 10% of the upstream's 80%, or 8%. So we have 20% multiplied by the difference between 38% and 8%, which is 30%. This gives us an additional 6% removal, leading to a total removal of 80% plus 6%, or 86.00%. Now consider this challenge. What would the total removal be if the upstream retention removal was 50% instead? It's important to note that earlier software and calculators often made a simplifying assumption that the decrease in a wet pond's effectiveness didn't depend on the upstream retention volume. This method presents a more nuanced approach. On this slide, we're examining a crucial concept in particle removal modeling, known as double dipping. This occurs when we incorrectly assume that the same particle mass can be removed both upstream and downstream in a sequential process. While it's not physically possible to remove the same particle twice, some basic modeling approaches can inadvertently make this assumption, leading to an overestimation of the total removal efficiency. The equation you see here, F1 plus 1F1 x F2, is an example of a calculation method specifically derived from equation 9.5 in AH Volume 1, where this double-dipping effect can manifest when the removal function is not properly adjusted for in such a series removal equation. It essentially double dips, giving us a falsely high removal efficiency by counting particles as removed multiple times that were only actually removed once. Here, we're comparing the total nitrogen or TN removal capabilities as predicted by two different software versions. The 2020 software, known as BMP Trains, and the upcoming 2025 software, BMPFast. Our scenario involves an upstream retention system combined with a downstream wet detention pond, operating with an average residence time of 31 days. The key difference lies in how each software models the interaction between these two treatment stages. The 2020 software assumed a constant decrease in the wet pond's removal efficiency, regardless of the design or volume of the upstream retention. Essentially, it treated that upstream treatment as a fixed, independent factor. In contrast, the 2025 software offers a more dynamic model. It predicts that the decrease in the wet pond's removal is a direct function of the upstream retention's characteristics. This newer software is also designed to support modeling upstream low-impact development or lid retention practices that might have lower individual effectiveness, such as tree wells and rain gardens, allowing for a more integrated and realistic assessment of the entire system's performance. When we talk about wet ponds, it's crucial to understand the concept of an irreducible concentration for certain pollutants. For total phosphorus, or TP, there's an irreducible concentration of 0.015 milligrams per liter that wet ponds simply cannot remove, no matter how efficient they are. Similarly, for total nitrogen, or TN, this irreducible concentration is around 0.400 milligrams per liter. However, our focus here is on TP because the maximum removal effectiveness for TN in wet ponds is usually quite low, less than 43%, making it less of a priority for these systems. Considering this irreducible TP concentration of 0.015 milligrams per liter, along with the event mean concentrations or EMCs from various land uses, we can determine the maximum removal efficiency achievable by wet ponds. A summary of typical EMC values for general land use categories, such as those found in the Applicant's Handbook Volume 1, helps us in this calculation. What we find is that the usual allowed removal by wet ponds, based on both the irreducible TP concentration and the land use EMC, is about 95%. This 95% figure is often the maximum specified percentage removal for performance standards. These maximum removal efficiencies can range from 91 to 97%, depending on the specific land use. For example, highway land use typically has the lowest initial EMC for TP, which means it also results in the lowest maximum removal efficiency within that range. We'll be using the BMPFast software to walk through an example project, and we'll show you screen captures of both the inputs and the resulting outputs. This particular example focuses on calculating the average annual removal achieved by a wet detention pond. It serves as a performance analysis to demonstrate not only the wet detention pond's mass removal capabilities, but also how it fits into a broader best management practice, or BMP, treatment train within the same catchment. A treatment train is typically employed in these scenarios because a single wet detention pond often doesn't provide sufficient pollutant removal on its own. Our project is situated in the southwest coastal area of Florida, a region that experiences an average annual rainfall of 52 inches, placing it within meteorological zone 4. Looking at the pre-development conditions, our 2-acre watershed is defined as general agriculture, with a pre-development pervious area curve number of 70. Following development, the area transitions to high-intensity commercial use. In this post-development scenario, we have a directly connected impervious area or DCIA, of 30.5%. The wet detention pond itself is 0.2 acres, designed with a permanent pool volume of 0.30 acre-feet. An important design note here is that this initial design features no littoral zone, which essentially means it has near vertical sidewalls. For the post-development conditions, the non-DCIA curve number is 77.8. This number is higher than the pre-development pervious curve number because it accounts for disconnected impervious areas, meaning some impervious surfaces are designed to discharge to pervious surfaces before reaching the pond. This reflects the option of disconnected impervious area in our input data. Finally, it's worth noting that this particular site does not discharge into an outstanding Florida water or an impaired water body. To begin, you will enter the necessary data into the General Site Information worksheet. Following that, you'll proceed to enter data on the Watershed Characteristics worksheet. It's crucial to understand that the post equals pre values, which establish the net improvement performance standard, are determined only after all the individual catchment data has been fully entered. A specific consideration involves wet ponds or wet areas that do not contribute annual runoff. If such an area is present and its total area is entered, you'll also separately enter the wet pond area. This ensures that the system correctly processes the data, preventing the runoff and loadings calculations from including the runoff from that wet area. When evaluating potential best management practices for a project, we might consider options such as wet detention, reducing directly connected impervious area, permeable pavement, green roofs, or surface discharge filters. For our example, we'll initially focus on wet detention. Once the data for the wet pond, including its permanent pool volume, is entered and the calculations are performed, the wet detention pond is then selected within the configuration or routing worksheet. It's important to note that a single wet detention pond often won't meet all the specified removal targets, such as both the percentage reduction goals and the net improvement goals. For instance, our example shows that the initial wet pond alone does not satisfy either the 55/80% reduction or the 77.3, 73.7 net improvement targets. In such cases, additional BMPs, like modifying the catchment's directly connected impervious area or incorporating other treatment measures, will be necessary to achieve compliance. This specific project example also illustrates how it's possible to meet one of the required percentage removals or net improvements, but not necessarily both simultaneously. The data for this scenario is derived from an actual ERP application, though we've altered the site location for this educational presentation. The current removal performance does not meet the required standards, even after we implemented a design change for the wet pond to include a littoral zone. Although the catchment characteristics themselves remained unchanged, the resulting annual removal is 39.7% for total nitrogen and 67% for total phosphorus. These figures unfortunately fall short of our specific removal standards, which are 55% for total nitrogen and 80% for total phosphorus. Furthermore, they also do not achieve the broader net improvement targets of 77.3% for total nitrogen and 73.7% for total phosphorus. Let's now consider adding a surface sorption media discharge filter. For this option, we've selected the Bold and Gold CTS media to be applied at a treatment volume of 1.5 inches. This filter is projected to achieve a 65% removal rate for total nitrogen and an 83% removal rate for total phosphorus. A key operational requirement for this particular filter type is the presence of an upstream storage pond to ensure a sufficient head for proper operation. Fortunately, our existing wet pond can effectively serve this storage need. However, it's important to note that even with the wet pond fulfilling the storage requirement, this option alone does not meet our overall net improvement target for total nitrogen removal, which is set at 77.3%. When we arrange a wet detention pond and a filtration system in series within a single catchment, ensuring there is no additional inflow entering between these two best management practices, we apply a specific series calculation to determine their combined effectiveness. This configuration, where the filter is situated immediately after the wet pond, is then entered into our routing catchment selection worksheet to define this multiple BMP combination. This particular setup yields impressive results: an annual removal of 78% for total nitrogen and 93% for total phosphorus. We then carefully compare these achieved removal rates to our established performance standards. For instance, if our standards require a 55% reduction in total nitrogen and an 80% reduction in total phosphorus, along with net improvement targets of 77.3% for TN and 73.7% for TP, we can confidently conclude that this wet pond plus filter system successfully meets both the specified percentage removal and the net improvement for both total nitrogen and total phosphorus. With this successful evaluation, the next step is to proceed to the catchment configuration and select this multiple BMP for routing. This slide provides a summary of our findings, much like a report generated for permit compliance or as a learning exercise. Our analysis shows that the combination of a wet pond and filter media successfully meets the required performance standards. In a detailed report, you would typically see a clear yes response indicating this compliance. It's also worth noting that while this combination works effectively, there are other treatment train options to consider, such as reducing directly connected impervious areas, incorporating permeable pavement, or utilizing green roofs, among others, to achieve similar or even better pollution control. Before you move on, or if you're stepping away, please remember to save your work. It's a good habit to save frequently to avoid losing any progress. So what have we learned throughout this module? We've gained a solid understanding of how to define and calculate the removal effectiveness for a wet detention pond. This includes appreciating how its annual effectiveness is determined under various design and operating conditions, considering factors like a littoral zone, managed aquatic plants, floating wetlands, and average annual residence time. We also honed our skills using the BMPFast software. This has equipped us with enhanced navigation and data entry abilities, crucial for performing average annual mass removal analysis and calculating volume discharges specifically for wet detention ponds. Through this, we've explored how annual effectiveness can change based on different inputs. A key concept we explored was how to calculate a wet pond's removal efficiency as a function of upstream retention volume, understanding how upstream practices can influence downstream performance. We used real-world example projects to illustrate these principles, demonstrating practical applications of our learning. An important takeaway is that a wet pond, when designed as a standalone system under normal conditions, often may not meet stringent performance standards on its own. However, it's crucial to remember that wet ponds are highly effective when integrated with other best management practices, forming a series of BMPs to collectively achieve higher total removal rates. We also noted that while upstream retention BMPs contribute to overall removal, they can paradoxically lower the individual removal effectiveness of the downstream wet pond. The BMPFast software, of course, serves as a valuable tool to assist in these complex calculations, especially when analyzing a series of BMPs. This concludes our discussion on wet detention ponds and how software tools like BMPFast can significantly streamline the process of understanding and filing permit applications in a timely manner. We encourage you to explore other learning modules if you feel the need for additional review, and consider applying to take the competency test. For comprehensive details on how to obtain a competency certificate, please refer to the dedicated learning module titled Self-Test. Thank you for viewing and listening to this presentation.